This is going to be a presentation on our polyatomic ions, which take a little bit to understand, but you can see the pictures of what we're going to be talking about now. This is kind of our hit list of easy ones. Now, when we're talking about polyatomic ions, you just look at the pictures of the compounds and don't think about the way that the space filling is drawn, but just counting. Binary compounds, which we've already talked about, are composed of only two elements, where ternary compounds have three different elements and include a polyatomic ion. Now, polyatomic ions are ions with two or more different atoms, and they form their own covalent bond that has an overall charge. And polyatomic ions can be thought of, like the sulfate ion, as a single unit for a lot of chemical reactions. So you'll have magnesium sulfate and it'll just look like that, and it can break apart into the magnesium and the sulfate, but the sulfate ion doesn't tend to dissolve in water. Now, you can find a list online. I Googled these guys up. Most of them end in ate or ite, and elements end in ide. Some of the really early ones end in ide, like hydroxide and where's the other one on this list? No, hydroxide's the only one here. So we have 7 that you'll come across fairly frequently because they're really useful, both for learning and for basic industrial chemical reactions. Our first one is ammonium, which is a NH4 and has a positive charge to it. This is what our ammonium ion would look like, and this is how you would draw it out in a Lewis structure. Second one is acetate. An acetate can look like this, which gets a little exciting, but it's the ion made when acetic acid loses one of its hydrogens. And you'll see it written out as CH3COO2. It can also be, CH3CO2. It can also be CH3COO or C2H3O2. In each case, you see it has missing just one charge, and this has a little resonance structure drawn in, while this has a single double bond. Both will work out. Hydroxide, this is one we'll see a lot. It's OH minus, and hydroxide is the basic unit of bases. It's a lot of things that are hydroxides turn out to be bases, chemically speaking. And you will see that it has the OH minus one right there. And when we write them out as a Lewis structure, we put a little bracket around it to show that they are a polyatomic ion and they are stuck together. Nitrate is next. That's NO3. It has this nice trigonal planar formulation here. Carbonate is CO3, and it looks like nitrate, but it has a -2 charge on it, and you get a little more of that resonance structure with the dotted line showing up right there. Sulfate is SO4, 2-, and our sulfate ion is the first one that has a real interesting three-dimensional shape, and I would kind of draw this in so that you can see it. So if I connect the middles of these guys in the back, it makes a triangle, right? But I have this other guy up front, so I'm going to use a more different color to connect 2 of the lines to him. And one more color, let's do, this will show up, this to this. So it does make a pyramid, but you see the pyramid is made of triangles, and you've got 1, 2, the one in the back that we can't see 3, and the one on bottom 4. And a 4-sided three-dimensional object is called a tetrahedron. So even though it looks like a pyramid, this guy is a tetrahedron. And we can find some apps online that'll rotate the guys. But like sulfate, the phosphate ion is also a tetrahedron. And you can see them drawn as Lewis structures. They have kind of 4 things out there. And three-dimensionally, this guy's rotated a little bit. So it's much easier to see that kind of tetrahedral idea. Oop, wait, let me get that out here. If I connect the dots on it and go from here to here, to here, to here, and then to the other guy is there, to there, And there. Yeah, something about the tip just makes that show up easier to me as having 4 sides to it. Phosphate is a -3, where sulfate was a -2. So when you do want to keep track of the charges, because the 8 part doesn't really indicate what charge it has to us. Now, I took the class through this when we were all here together, but I would say how many ions are present. And it's really easy to look at the brackets and just kind of count how many you have. So like this guy has 3 brackets, so that's pretty easy. The first one, KOH, that's very easy. There's just 2 ions, but you just count. Use your fingers. It's not that exciting. When we take it off of this bracket notation, trying to kind of circle the polyatomic ions as they exist and count the number of ions, this is a little bit more thinking, but if I get my circle tool out, I know that the OH is an ion, so I can do that. And it takes a little bit of thinking for some of these, but if you see that they have the ion itself in parentheses, that's a pretty good sign that that's a polyatomic ion right there. So we have the OH, the SO4, and it's got 3 ions because it has 2 sodiums and 1 sulfate on it. With this PO4 being bracketed, that's an indicator that that is its own ion. And if we count, we have 3 calciums and 2 phosphates, so that comes out to 5. The tricky one is ammonium hydroxide. And then we just have an ammonium example there. And that's our only positive ion that we deal with a lot in class. So you just get used to seeing the NH4, where everything else is an anion, a -1, and it comes at the end of our notation. Now, when we name these guys, it's just like naming other ionic compounds. You say the name of each ion. So Na is sodium, NO3 is nitrate. This is again a sodium one, but the CO3 is carbonate. And then these guys get a little more practice. Na sodium, OH hydroxide, Mg is magnesium, and this long chunky boy is acetate, magnesium acetate, and there's our tricky ammonium chloride. Writing the formulas, you can take the name and count the ion charges, just like when you write ionic formulas out from the name, and you write it out, and you can do the thing where you crisscross the charges to see how many of each are going to fit there. So this is all kind of review, but we just have to remember some of our most common ions as we go in, so we know what a hydroxide and a phosphate looks like. And it's not the end of the world if you have to stop and look them up. In the classroom, I have textbooks I'll show you that have all of the names in them. So I hope that this has been useful for you, and I will see you in class.